that the stress strain diagram will be something like this for elastic region. Okay, and then so it is going from A to B.
सर आ रहा है तुम्हारा या तो उधर से या तो इधर आ जाओ
And when
ठीक
you
अब सही
unload it, then it will follow the same path. So it will be just AB and then BA, right? But if I apply the force sigma at a very high rate, then it will not get the whole strength, but it will get something lesser than what it achieved at isothermal condition. Okay. So isothermal meaning that all the events which are happening inside the material are in equilibrium with the surrounding. Okay. So if I apply very fast the force or displacement on it, then it will not achieve the strain it would have achieved in case of isothermal loading. And then you leave it for some time without application of any incremental force. So thus this force is applied, and then with time it will achieve this. Do you understand? So even for the regime where we have metallic materials, if you apply a very high force, so with a very high strain rate, then the strain will not be as much as it would have been for the isothermal condition. And then you leave it for some time and it will achieve that. Okay? So it will come in equilibrium, and then when you unload, if you unload faster, then what will happen? It will come here and then it will relax. So not all the part will be recovered instantly. Some of the part will be time dependent. Okay? And this can happen in any material. Okay? And similar to fatigue, if you keep on applying this thing on a cyclic way, then you generate a hysteresis loop, and tensile deformation increases the temperature of the material, and compressive forces will decrease the temperature of the material when your rate is very high, meaning it is adiabatic condition.
very fast
Okay. So you are not allowing the time for the dislocations to move as they would if there was enough time. So everything is time dependent. It depends at what scale we are looking at and at what scale we are at. Okay. So for example, when we talk about higher dimensions, then more than 3 dimensions we cannot see. But it is also possible to not be able to perceive the same dimension at a very large scale. So for an ant, it is not possible to fathom the difference between Alaska and Ecuador or some other country, because for ant that's a huge dimension, and that perception is not possible for it. Although even if you imagine the ant to have the same senses as us, so we cannot fathom how large the universe is. We are still progressing and trying to understand how large it is, but we don't know. Okay. So any material can show this effect. It depends that how faster you have to go in order to achieve any significant amount of effect on this. So this, whatever energy is dissipated in this hysteresis, is very small for metallic materials. But this helps for polymers to dissipate the vibrational energy, okay, for damping. And this is called an elastic effect. and the relation can be written as the rate of change of temperature with respect to strain is the molar volume, thermal coefficient of expansion, elastic modulus, temperature and specific heat. Okay, so any positive increment in this will decrease this term, so that will cause lowering of temperature. So then I mistakenly said that any tensile deformation will cause lowering of temperature, lowering of sample temperature. It will cool the sample temperature. And any compressive, so when this becomes negative, then what will happen? So all these things are positive, okay? So when this becomes negative, that also has to be negative, okay? So if we are starting at some temperature T, reference temperature, and whatever is the final temperature, that, and then we have delta epsilon is equal to something positive. So that means that is greater than 0, right? So if delta epsilon is negative, that means this term has to be negative, right? So if this is less than 0, that means T reference will be less than Tf. That means the final temperature will be lower. So again, I came back to my first statement that compression will cause lowering of this temperature. Okay, so this is the relationship. So the essence of this is that adiabatic deformation can cause a change in sample's temperature. Although this change in temperature, first of all, it depends how much delta epsilon you are applying. Okay, and this is not very high value, but you can imagine that if something is broken at a very high speed, then sample feels it in the form of temperature, and temperature and strain rate effects are equivalent to each other. Okay, whatever happens in materials due to change in strain rate has been also achieved by changing the temperature of the material. So increasing the strain rate is equivalent to decreasing the temperature. Okay, if you increase the strain rate, the material becomes brittle, and if you decrease the temperature, the material becomes brittle. Okay, and all this is happening because the major mechanism involved in these deformation is diffusion, and diffusion is happening at any point of time, any point of temperature. Of course, we are not talking about absolute zero. So then what is happening when you are increasing strain rate? Then diffusion is a function of time and concentration. Okay, so diffusion will not be possible if you don't provide sufficient amount of time, right? So if you increase strain rate, time is not available, diffusion will decrease, and if you lower the temperature, diffusivity will decrease, right? So diffusion is a function of the probable correct jumps an atom is making in the direction of an available vacancy for substitutional diffusion. Okay, so if an atom is sitting, then it is jumping in all the directions. So in any direction, the probability of jump is total probability divided by 6, total number of jumps divided by 6, right? So that many number of average jumps it is making. Okay, and then you have to have a vacancy in, so if you have a vacancy here, only then, so this has a probability to jump in all directions. Okay, and then if it makes a jump in this direction and there is a vacancy here, only then diffusion will happen, right? So this jump probability is a function of temperature. As you increase the temperature, the amplitude of jump and the frequency will change. Okay, so as you go lower, this amplitude is going to decrease, the frequency is going to decrease, the jumps are not going to be that much. Even if there are vacancy available, diffusivity is going down.
So equilibrium number of vacancies also decreases with respect to temperature.
Yes, that also happens. So that will also contribute to lower diffusion at lower temperature. You are right in that. So one of the manifestation of an elastic effect in metallic materials is the time dependent behavior, which we call creep. Okay, and creep can happen by, so like plasticity happens by the movement of dislocations, and sometimes coordinated movement of atoms, fractional movement of atoms, like twinning. Okay, so creep can happen also by a few mechanisms. What are those mechanisms? So what is creep? Creep is time dependent deformation, but it is deformation. Okay, so it means you need to apply some force. So when you apply some forces, then dislocations should be moving. Otherwise it will be elastic deformation. So if the dislocations are moving, and then they will get blocked, and then you will have to apply more forces to break those barriers and to obtain further deformation. Time dependent deformation means that for the same amount of force, if you change the time, then deformation will be more. Okay, so if I hang something from a wire, it is not going to break. I don't think there will be any time dependent deformation in this case, or will there be? There will be.
At elevated temperature there will be.
Yes. Okay. So now we are coming somewhere. So at room temperature, this is not going to do anything. Okay. So when we elevate the temperature, that's a condition, no? So you elevate the temperature, then you see the difference, or you see the time dependent deformation in your time scale. Otherwise, 4, 5, 40, 50 generation has to die to see any effect in this. Okay, so maybe if there is a court case that this wire and weight belongs to so this brother and that brother, they are fighting the case, then probably after 3, 4 generations this will break.
Negligible creep.
So the litigation for wire will go on. Okay. So why temperature is important, and why when we provide temperature, then we can see the time dependent deformation in materials. So one thing is pretty clear, that temperature is providing or assisting diffusion. Okay. So diffusion, what will diffusion do? Also vacancy. What will they do to assist the time dependent deformation? So if I elevate the temperature, why this wire will elongate? What will happen because of increasing the temperature?
इंटरमोलिकुलर फोर्सेस कम होंगे और इंटरमोलिकुलर डिस्टेंसेस ज़्यादा हो जाएंगे बिकॉज ऑफ इंक्रीजिंग टेम्परेचर सो दे विल ट्राई टू एक्सपैंड
More climb will be there with the.
You should have raised your hand when I asked for best student. Yes. Yes. Dislocations are blocked. Okay. And they are not able to move. And then there will be nothing happening. After 10 kg of load has been applied, some dislocation has moved, some deformation has happened. That is in the form of instantaneous strain. Now they are blocked. Now they cannot move. Okay, they have the tendency to move, but there is a barrier, and that barrier can be broken by increasing the stress or by providing a different path to the dislocation. Okay, and second phenomena will be happening when you provide when you facilitate diffusion. Okay, so vacancies do not need stress. That stress is there. They just have to go to the dislocation, and with increase in temperature, you are increasing the equilibrium number of vacancies in the system, and vacancies will move to the dislocation because there is a stress field there. Okay, and at the core of the dislocation there is a high stress field. So there is a gap, there is huge distortion at the core of dislocation, and the atoms can move through it. Also vacancies can move through it. If atoms are not moving, what is their vacancy? Okay, so more vacancies can come, and they can lower the stresses, and thereby dislocation can climb up. Once it climbs up, then the barrier is not there, and then there is a stress. Okay, so shear stress is applied in whatever direction, and you have a dislocation, and that dislocation is blocked because here you don't have a precipitate, you don't have the planes or atomic structure to move. Okay, so dislocation has just come here and it is now blocked, it has no place to move because there is a precipitate which has a different crystal structure. Okay, so what happens now? Vacancies come and it jumps, it comes, and then it goes here, and now it can move. And that stress is still there. That stress was still there, but it couldn't move because kidhar jaunga main? So now there is a place it will move. Okay. So this is why when you elevate the temperature, not because of this reason, but chocolate will become softer, right? And if you cool it down, put it in the fridge and then break it, then that's a different mechanism. And if you put it in sunlight and break it, that's a different. And if you just break it, it will just flow. You don't have to break it, just put it in heat and it will flow. Okay. So as long as the so when most of the deformation which is coming in the metallic material for a constant load, which change in time because of Klein phenomena, then the rate controlling step is not diffusion, but it is Klein. Okay, and how do we describe Klein? For describing Klein, we need vacancies. Okay, so first of all we have to see that what can happen when we, and why do we say that when we have to apply constant force? Why do we say that? If I apply changing force, then creep will not happen. Okay. So then why do we need constant force?
So in changing force, deformation will be there because of increasing loads.
Yes.
And creep will also be acting.
Yes.
So then we cannot distinguish between.
Yes. Yes. So to isolate the effect of time in comparison to strain hardening effects, so time dependent and time independent phenomena both can happen simultaneously. Okay, and both do happen simultaneously. But in order to dissociate these two and see isolated the effect of time only, you need to apply a constant force. Okay, ideally you should apply constant stress, and there are machines which can apply constant stress, which acts on a feedback system. So you have an extensometer and that gives you the value of the current area. From that area it calculates the stress, it drops down the force, then again there will be some change and it will keep on doing it. Okay, but cheaper machines which we will have will only apply constant load. So when you put a tensile sample and you apply a constant load on it, okay, then as soon as you apply it, it will elongate. Right? It will elongate at t is equal to 0 as soon as you put the load. And after that you wait, and then it will keep on elongating, and then it will neck, and then it will break as the time increases. Okay? So if you plot this, so you don't need to plot the value of stress because that is not changing. Engineering stress is not changing. Okay? So what do you need to plot? You need to plot strain and time. So at time is equal to 0, you had some amount of strain, instantaneous strain, which is time independent. Okay? And after that, with time the strain develops, and then the strain develops at a very high speed and then it fades. Okay? So if you plot, and when you increase the stress, this curve will show different behavior. If you lower down the stress, then you will see something like that. And when you increase the stress, then you might see something like this. Okay? So 1, 2, 3 and 4. And if you plot the strain rate for these 4 curves, then how will they look like? For the first curve, the strain rate initially, so the slope of this curve initially is very high, okay, and then it is decreasing, then it is decreasing, and then it is decreasing, right? So the strain rate for the first curve is decreasing, and then what happens to the slope? It becomes constant, okay, so it becomes constant for a longer time, and then what happens to the slope here? The slope is now increasing, right? So it will be something like this. What will happen to the second one also? So the strain rate will decrease, and then it will be constant for some time, and then it will increase like this. What will happen for the third curve? And what will happen for the fourth curve? So what is the change when we increase the stress? What changes do you observe when you change the stress? This is for curve 1, this is for 2, 3 and 4. What do you see?
So strain rate at every with respect to time increasing with stress as we are increasing the stress.
As we are increasing the stress,
Strain rate is increasing for particular.
also decreasing now. Strain rate is also decreasing, also increasing.
No, I am comparing all the all the plots. For example, with respect to 1, in case of 4, the strain rate for every
Okay, fine. Then any other difference?
Sir, at very high stress, there is no time for strain rate to be constant.
There is no time for the strain rate to be constant.
Yes, sir. Strain rate is directly increasing without there is time left. Yes.
Worst student. क्या ऑब्जर्व कर रहे हैं आप?
At very high stress level, there is no decrease in constant and increase, only increase.
Correct. ये सही observation. So different features are not visible. They are getting suppressed. Right? So there is a region where the strain rate is decreasing, there is a region where strain rate is constant, and there is a region where strain rate is increasing. These 3 different phenomena are happening, and not all of them are observable at every stress level. Right? So what could be the reason for that? So first of all, why the strain rate is decreasing? What is the meaning of decreasing strain rate? Or if you want to answer the first question, why it is decreasing?
Sir, strengthening mechanism is going on inside the material.
Hmm?
Sir,
More constraint is there.
Hmm?
More constraint is there due to strengthening.
More constraint is there.
सर जैसे वो होता है ना कि मतलब पढ़ा था ऐसे कि जैसे आपकी वो नेक बननी शुरू हो जाती है तो उसमें जो आपके जो मटेरियल है जो आपका डिफॉर्म नहीं हुआ है उसकी वजह से ज़्यादा कंस्ट्रेंट आना शुरू हो जाता है नेकिंग में.
पर नेकिंग के पहले ही हो रहा है ना ये सब. तो नेकिंग तो यहाँ कहीं होगा.
डिसलोकेशन इंटरेक्शन.
हम यहाँ की बात कर रहे हैं. तो यहाँ पे क्या हो रहा है?
स्ट्रेन हार्डनिंग.
स्ट्रेन हार्डनिंग हो रहा है.
डिसलोकेशन इंटरेक्शन.
डिसलोकेशन इंटरैक्शन. बस डिसलोकेशन इंटरैक्शन.
So jokes and kings are getting formed.
That is the answer of dislocation interaction. उससे जो organ king बनता है.
Strain hardening.
Okay. So
Mechanism.
strain hardening is happening, but why that will decrease the strain rate? Is it obvious enough, or do you really understand? Strain hardening हो रहा है, तो strain rate घटेगा बढ़ेगा?
डिसलोकेशन डिफिकल्ट हो जाएगा डिसलोकेशन की मूवमेंट्स.
तो strain rate
कम
घटेगा
होगा.
कि बढ़ेगा?
कम होगा.
क्यों कम होगा? क्योंकि डिसलोकेशन का मूवमेंट डिफिकल्ट हो रहा है.
रिस्ट्रिक्ट हो रहा है.
Is there a relation in form of equation? What is the relation between strain rate and velocity of dislocation?
सर रिलेशन तो है डिसलोकेशन.
Yeah. So strain hardening is happening. Fine. Anything else is happening? Climb हो रहा है कि नहीं? Climb हो रहा है कि नहीं?
सो क्लाइंब
sir,
होगा तो
with increase of temperature. Sir,
ना
after some
temperature
time-
constant है. It is
Constant.
elevated temperature. One test. Different stresses. Climb हो रहा है कि नहीं? How many of you think climb is happening? Raise your hands. None. How many of you think climb is not happening? Raise your hand. None. मतलब कुछ पता नहीं.
सर हो रहा होगा शायद क्योंकि
हो रहा होगा शायद नहीं. मेरे कॉन्फिडेंट आंसर चाहिए. हो रहा है कि नहीं हो रहा है? हाँ कि ना?
यस सर.
सर
Sir,
नहीं. नो. आप सही. आपका नाम क्या है?
सवितेश.
सविकेश.
सवितेश.
सवितेश. सही. क्लाइंब हो रहा है कि नहीं हो रहा है?
नहीं हो सकता.
नहीं हो रहा है. नहीं हो रहा है. नहीं हो रहा है. हो रहा है. नहीं हो रहा
तभी
है.
तो
तुम
strain-
बोलो. नहीं हो रहा है. क्लाइंब होने के लिए क्या चाहिए?
वैकेंसी.
और क्या चाहिए? डिसलोकेशन. और क्या चाहिए? स्ट्रेस. और क्या चाहिए? बैरियर. इसमें से क्या नहीं है जो क्लाइंब नहीं होगा? ऐसा क्या चीज मिसिंग है कि क्लाइंब नहीं हो सकता?
स्ट्रेस भी है, डिसलोकेशन भी है, सब कुछ है.
सब कुछ तो है. फिर क्लाइंब क्यों नहीं हो सकता? क्या नहीं?
इंक्रीज स्ट्रेस नहीं है.
इंक्रीजिंग स्ट्रेस नहीं है, पर स्ट्रेस इनफ है डिसलोकेशन को मूव करने के लिए. और क्लाइंब यू डोंट रियली नीड एक्स्ट्रा फोर्सेस.
होगा सर क्लाइंब तो
तुमने तो हाँ ही बोला है पहले भी. So you are not changing.
रिलेशन होता है ना इक्विलिब्रियम नंबर ऑफ वैकेंसी और नॉर्मल स्ट्रेस का भी रिलेशन होता है ना.
Your answer you have not changed, no? Yeah, so that is okay. I am asking those who have said no. Majority of the people have said no. So I am asking what is missing? Why climb cannot happen? ऐसी क्या चीज नहीं है जो क्लाइंब नहीं हो पा रहा है? क्यों बोला नो?
क्योंकि सर अगर क्लाइंब होता है तो डिसलोकेशन मूव करता और डिफॉर्मेशन होता है।
हाँ,
यहाँ पे स्ट्रेन कांस्टेंट है, मतलब क्लाइंब नहीं हो रहा है।
स्ट्रेन कांस्टेंट है
मतलब उस रीजन पे ना जहाँ पे स्ट्रेन कांस्टेंट है।
इस कर्व में। कहाँ स्ट्रेन कांस्टेंट है?
इससे पहले इंक्रीज हुआ, फिर कांस्टेंट हुआ, फिर इंक्रीज हुआ ना।
ये स्ट्रेन है,
हाँ
ये
strain।
कांस्टेंट नहीं है। ये कांस्टेंट होता तो एक पॉइंट होता है ऐसा, नहीं ऐसा नहीं है, ऐसा।
ऐसा।
हाँ वैसा ही है एक्चुअली।
वो तो सेकंड रीजन होगा।
सो स्ट्रेन कांस्टेंट है, सो व्हाट आर यू सेइंग? से इट अगेन।
सर वो अगर डिसलोकेशन जंप कर लेता तो फिर उस डिसलोकेशन मूव करता, फिर उसमें डिफॉर्मेशन भी होता। बट यहाँ पे स्ट्रेन कांस्टेंट है।
So that is in the second region.
सेकंड रीजन।
मैं तो पहले वाले की बात कर रहा हूँ जहाँ स्ट्रेन हार्डनिंग हो रहा है। यहाँ तो स्ट्रेन हार्डनिंग भी नहीं हो रहा ना। तो पहले वाले रीजन में क्लाइंब हो रहा है कि नहीं? हो रहा है कि नहीं हो रहा है?
सर स्ट्रेन इंक्रीज कर रहा है बट डिक्रीजिंग स्लोप के साथ, तो क्लाइंब होना चाहिए।
ये तो कोई लॉजिक नहीं हुआ। डिक्रीजिंग स्लोप के साथ तो मतलब स्ट्रेन हार्डनिंग हो रही है, इसलिए स्लोप डिक्रीज कर रहा है ना। हाँ। बताओ। There is no reason why climb cannot happen, except time is less. But that doesn't mean climb is not happening. Climb is happening. Strain hardening is also happening. Climb is also happening. If the temperatures are very high, then grain boundary sliding will also be happening. Okay. And then stress induced diffusion will also be happening from grain boundary and within the grains. All those things are happening. It is a net result which you are seeing. Okay. So effect of climb is not very high at smaller values of time, because that's a diffusion controlled process. So that effect will become significantly larger. Either you decrease the stress, or you increase the time, or you increase the temperature. Not necessarily a thumb rule. If you increase the temperature to a very high value, then the mechanism will change. Instead of climb, something else will start happening, and climb will be suppressed completely. Okay. So in the first stage also climb is happening, also strain hardening is happening. The net result is that strain hardening is more.
Dominated.
So more number of dislocation barriers are there. They are created by their own. Okay. In comparison to the number of dislocations which are climbing and finding another path. Okay. Then what happens in the second region here is that there are two mechanisms, and these two mechanisms are facing each other, so they are exactly opposite in nature. So there will be a point where they will both be of equal strength. Okay, that time has to come, because it's a game of time. So as you increase time, the diffusion based phenomena will be increasing, and there will be a point, because it has to cross it. So there is a route here. Okay. So it has to cross it. So there will be a time when the diffusion based phenomena will have the similar effect as the strain hardening things are having. Okay. So strain hardening will be compensated by the phenomena of recovery. So dislocations will be arranging themselves, not only climbing, they will be arranging themselves, they will be forming cell structures. Okay. They will also be climbing, and that's how they will be forming cell structure. So they will be compensating with each other, and this is happening not statically. So it's like recovery is also happening, and strain hardening is also happening. So it is called dynamic recovery. Okay, and this is being compensated in some point of time where the strain rate becomes constant. Okay, so here not necessarily this is a horizontal curve. Okay, in this part it can be a linear curve. For which the strain rate will be constant. If it is a horizontal curve, strain rate is 0. Okay, so then it will be touching here somewhere, the x-axis, the time axis. Okay, so this is the reason where both of the mechanisms are acting against each other, and both of them are equal in strength. And then of course you have not changed stress, so that part of mechanism is not getting strengthened. What is getting strengthened with time is diffusion based mechanism. Okay, so that will take the lead beyond this point, and then those mechanisms will be so high that then there will be damage now. So the strain will be so high that material will not be able to accommodate that much amount of strain, and then there will be void nucleation, growth, coalescence, and quaking. Okay. So based on these observations, this curve is divided into 4 regions. Okay, the first region is called the instantaneous strain part, and this is really not a region in US and other countries, but this is taken as the first region or stage 1 in UK. And the second region, which is called primary creep region, where the strain rate decreases and strain hardening is more than recovery. That region is called stage 1 or primary creep. And then you have the second part where strain is kind of linear with time. Okay, and then you have the part where exponential growth in strain happens, and this is your tertiary part. Okay, so this is tertiary creep, this is secondary creep, and this is primary creep. So in primary creep, strain rate is decreasing, in secondary creep, strain rate is constant, and in tertiary creep, it is increasing. Okay? Okay. So in certain cases, this time dependent deformation can be climb controlled. Okay, the rate controlling step is climb. It doesn't matter. So what is the rate controlling step? If there are 4 things happening, then which one is rate controlling?
Climb. Most dominant.
If there are 4 things, not about creep. Okay, A, B, C, D. 4 things are happening. Which one will be the rate controlling thing out of A, B, C, D?
Dominant ones are this.
No. So you might have read in your textbooks, the slowest event is the rate controlling event. Always, not the dominant one. The slowest one. Right? Why? Why slowest?
Because other activities depends on that.
What?
For example, in a sequence,
Yeah.
if you have to make something,
Yeah.
अगर हमें कुछ बनाना है तो जो एक्टिविटी सबसे स्लो रहेगी
हाँ.
अगली एक्टिविटीज उसी पे डिपेंड करेगी. मान लीजिए कोई भी चीज़ बनानी है अगर हमें.
Right? Why the slowest is the rate controlling step?
So slowest will be the deciding factor.
How? It will be deciding what?
सर जो भी मैकेनिज्म होगा वो स्लोएस्ट से ही डिफाइन होगा ना, तभी उसी को कहेंगे कि वो रेट कंट्रोल करता है.
कोई एग्जाम्पल है?
जैसे मान लीजिए सर 4 लड़के हैं, यहाँ से निकलना है सब बाहर.
करेक्ट.
3 लोग तेजी से निकल गए.
करेक्ट.
मैं सबसे स्लो निकला.
करेक्ट.
तो रेट ऑफ एग्जिट
हाँ.
मैं ही डिफाइन करूँगा ना सर.
रेट ऑफ एग्जिट नहीं डिफाइन करेंगे आप. रेट ऑफ एग्जिट तो आपकी अपनी है, बाकी 3 लोगों की अपनी है.
और
आप ये इवेंट डिस्क्राइब करेंगे क्लास कब खाली हो गया. Okay, so that's why slowest is the rate defining step. So if climb is the rate defining step, then in that case strain rate has been correlated in this form. This is not primary key. This is also not secondary key. This is just a power law correlation. Okay? And it has been given by Weitman and Frank. It follows Norton's law. So it is called Norton's law. Okay? Or power law. Okay, in this case B can be defined differently. So B can have different meaning, N can have different meaning. Okay, and if this is followed, then strain rate is not a function of time. Right? In this law, strain rate is not a function of time. So this mostly will be happening in why mostly? It will be happening in secondary key only. Right? If you have to make it something like this for primary, then you have to make N or any of the other parameters time dependent. Then it will be describing different stages of the. Okay. Apart from this, so how you can find it? This is a very simple example. So you can find out B by plotting log and log of this, and find out the slope. That will be N. Intercept will be defining B. Okay. Yeah. Good. How much time do we have? We have 3 minutes. So then what other thing can happen is that you can have stress induced diffusion. Okay, and for diffusion you need vacancy and you also need dislocations. So one concept is that vacancy interstitial pairs are created in the system. Okay, this is a weird concept. So out of nothing something happens. In one of the thesis proposal this question was asked, that if you have a perfect crystal, then how the dislocations will come up, how they will come up. So similar to that, if you want to create a vacancy, you will also have to create an interstitial so that it can nullify. If you create a positive charge, you have to have a negative charge. If you have to have a dislocation, you have to have another dislocation in the opposite direction, which can nullify. So if you have a dislocation like this, you will have to have a dislocation like that. Okay? So when they will join together, then there will be a perfect crystal. So from a perfect crystal, 2 dislocations can come up. This is the homogeneous nucleation of dislocation. Okay? You can have heterogeneous nucleation of dislocation, for example, on the semi-coherent precipitate interface. When a precipitate is transforming from coherent to semi-coherent, then one-on-one correlation of atomic planes are breaking at certain locations. Okay, and that will create some dislocations there. Okay, so the energy required for a diffusion and an interstitial pair to evolve in a system is larger than the energy required for the vacancy to appear from grain boundaries. Okay, so theoretically the energy which is required for a perfect crystal to give a vacancy substitutional pair, that energy is much larger than a vacancy which can come up from a grain boundary, and also it can absorb atoms. Okay, so it can do both. It can produce dislocation at grain boundary, can act as a source of dislocation. Okay, it can absorb dislocation, it can create vacancies, it can absorb vacancies. It can do all those kind of things. Okay, so in certain cases grain boundary decides how much of diffusion based phenomena can happen, because that is defining that how many vacancies can come up and how many dislocations can be absorbed and things like that. And grain boundary, apart from, so what is happening in Klein, the diffusion is happening through the core of the dislocation, which is pipe diffusion. Okay, if the diffusion happens on grain boundary, then it matters that what is the grain size, because the slowest process for an atom will be to go from the center to the grain boundary. Okay, so the grain boundary size will be describing the diffusion phenomena which is based on the grain boundary. It will also be defining the diffusion which is happening through the grains. Okay, so similar to self diffusion. We will discuss this in the next class. Okay.